Okay, so my name is Samin. I work at Microsoft Research. And as Andrew said earlier, I use ideas from mathematics to make sure that programs, so software and hardware, for instance, don't crash. Okay? And now we've had some really great talks this morning, ideas about psychology or machine learning, biology, and tracking. And how do we make these ideas part of our physical kind of world? How do we make them into some hardware or some software? Well, we write programs to make these ideas into something that we can kind of control or touch. Okay, so I'm going to be talking about programming and programs, and we're going to write a little program and kind of see how it goes. Okay, so who's done some programming here? Okay, that's great. That's great. So we're gonna do something like that. Okay, and I'm going to take you with me talking about a particular program and implementing it using kind of a particularly advanced language that comes out of Microsoft. Okay, so but let's start before we talk about programs. Let's talk about something nice and shiny. Okay, this is actually the phone that one of the speakers is going to send up in a balloon. It's the Nokia Lumia. And it's a really shiny object. Maybe you've got one like this, or an iPhone or a BlackBerry. It's a really nice shiny object. But what makes the phone shiny? What I've called it now is the phone stack. Okay, there's the shininess of the phone. The life that comes from it comes from a stack of computer programs. So let's look what this stack is. At the bottom of the stack, there's hardware. Okay, I've just written HW here. It's hardware. Above hardware, there's the operating system. Okay, these are both computer programs. Okay, we don't see them. All we see is the shiny object. Above the operating system are your apps. The apps is what you see. But all of these three things, they live on top of each other, and they are computer programs. Just to get an idea, the hardware is written in a programming language called Verilog. And Verilog is a really low-level language, and it's used to design hardware, really deal with logic at a very, very low level. Above that, the operating system, that too tends to be written in a very low-level language called C. And C is really good for controlling hardware, so controlling the things inside your phone, like when you press a button, when you send a text message, all of these things, that's what the operating system does. And above that, the apps. Well, the apps, lots of people write apps. And you can go to phone marketplaces and get apps, and you can very, very easily write apps, because they tend to be written in a very high-level language. And here, I've shown a bit of F#, and we're going to look at F# in a while. Okay, so that's the phone stack. It's a shiny object, but what gives it life is the programs inside it. And we, as computer scientists, we write programs, and we bring these things to life. Okay, so let's look at one of the apps on the phone. So this is on the Windows phone, and this app is the People app. And the People app is like your phone book or kind of directory. But can tell me something? Can anybody in the audience tell me, is there something wrong with this app right now? What it's showing us. Is there something wrong? Yeah, the boy there? Actually, I can't hear. But that's right, yeah. So if you can see here, the names are not sorted, right? R comes after S. The S's are in the wrong way from what we expect. Sorting, that's what we would normally see. Sorting is a very essential, very fundamental idea. And we don't even consider how things are sorted. And how would we write a program to sort things? So that's what we're going to look at in the rest of this talk. How do we go about doing some sorting? Okay. So in particular, the program I'm going to talk about is something called Quicksort. And as you can see from the subtitle of my slide here, Quicksort was invented a long time ago, in 1961, by Tony Hoare. And Tony Hoare is actually a researcher at Microsoft right now. And even though it was invented a long time ago, it's such an elegant and such a fast computer program that people still study it. And they still think, why does it work so well? And so we're going to look at quicksort. So the beauty of quicksort is that it can be described really, really easily in words. Okay? So I've got a list to sort this list, and I've called this list L. Okay? Because when you begin writing computer programs, you don't talk about the list 1, 2, 3, or the list, A, B, C. You talk about an arbitrary list, and that's where kind of ideas of algebra come in. So there's an arbitrary list called L, and in order to sort it, this is what I have to do. The first thing, I pick an element of it, and I call it the pivot. And using this pivot, I make two lists. First of all of those that are less than the pivot, and on the other side, all of those that are greater than the pivot. Okay? And when I've got these two lists, I apply this idea, this algorithm, this program, quicksort, to each of those ones, and actually then I'm done. And this is the basic idea in quicksort. Okay? So actually what we're going to do is, I think it's such an easy thing to write a program of, and such an easy thing to understand. We're actually going to kind of run a live demo of this. So actually I need 7 people, and I'm going to be the program, and you guys are going to be the list who are going to be sorted. Okay, so so I'm going to avoid the bias here again. I'm going to go to the back. So let's have you. Yep. You've been there already. Let's have you. No, girl right in the front. Yep. Yep. 2, 3, 4, 5, 6. Both of you. And 7. Okay. Actually, I think we'll be all right. Okay, now, what we're going to do, these guys are going to be the element in the list, okay? So your element number 6, okay? And your element number 2. Okay, ignore the big thing. This is one basic idea of computer science, is that you concentrate on something really important, like the small number in the corner, okay? Because the big thing is not actually important right now. Okay, your 7, your 3, your 5, 1. Oh, are there 2 there? Oh, okay. Okay. So both of you can be 4. Okay, so we're going to run this program on this list of people. Okay. So first of all, let's pick a pivot. Any volunteers for choosing a pivot? 3, somebody said. Okay. So, or 1, somebody said. 3 will be more interesting, I think. So let's choose 3. So he's the pivot. So if you step forward a bit, okay. So he's the pivot. Now everybody who's less than 3, come to this side. Come to his right-hand side. Everybody who's greater than 3, go to the other side. Okay, no, don't. You can stay there. And say you didn't happen to come there, but in fact you came there. I'm just going to make it a bit more difficult. Okay, so now he's the pivot, and we've got all the people who are less than him on this side, all the people who are greater than him on this side. Now we do the same thing to these sublists, okay? So we pick a pivot. Let's pick him, okay? If you're in this list, if you're less than him, go to this side, go to his left. Okay, and then we're done because there's nobody else there. And we'll do the same on the other side. Let's pick a pivot. Let's pick 4. You 4, yep. So if you're less than 4, come to this side. Yeah, good. And everybody greater than 4 is on that side. Okay, so then we're kind of done. We've got this list left. So let's pick 5. So if you're, let's pick 6, actually. And that's bad as well, actually. Okay, let's go, if you go here a bit. Okay, good, okay. So let's pick 5 as a pivot now. So 5, if you're less than 5, come to this side. If you're greater than, go to that side. Okay, and if you shuffle up a bit. And are we nearly done? I've run out of stage. Okay, and then we're sorted. Okay, so thank you very much. If you just place the, give these back to me. So you see, the idea of quicksort is really, really quite simple. And there's some really basic ideas, like I've written recursively up there. And recursively just means apply the same thing again to the smaller object. So I just want to show you again what happened there. So if you couldn't see from the back, just want to show you again what happened there. So here was our list. I picked a pivot, 6, say. Now I'm going to put everything that's less than 6 on one side, everything that's greater than 6 on the other side. So let's do that. So everything less than 6 on this side, everything greater than 6 on the other side. And now those two lists, the ones that I've just marked here in blue, I'm going to quicksort those. Okay? So I quicksort those. They're sorted. We're done. Okay? Why I wanted to show you this picture is because in my work as a computer scientist, I use pictures a lot. I use complicated pictures of trees or graphs, and these pictures often have some kind of property. And actually, the picture Torres showed us this morning, the graph of his score, that was a really interesting graph because it had some property. You know, all the numbers on a point added up to 100. Had a really, really interesting property. These pictures have really interesting properties. For instance, this one has the property that everything on the left of the pivot is always less than it. Everything on the right of the pivot is always greater than it. Okay? And these properties help us convince us or allow us to prove that the programs we are writing do indeed do what they're meant to do. Okay, so we've seen quicksort in words, and we've seen quicksort as 7 people. So let's actually look at some code now. So I'm going to write quicksort in a programming language called F#, and you too can try this out. There's this website called tryfsharp.org, and you can go there, and we'll see what it looks like, and how you can just write your program and you can run it. Okay, so this is try-F#, and I'm just going to go to the begin button. And normally you go through it and it gives you a tutorial, but I'm going to skip the tutorial. I'm just going to go to have one window. So I'm going to click this one window. So as you can see, so now we have 2 windows here. The top one, where we write our program, and the one underneath, where when we press run, the program will run. Okay, now I'm going to cheat a bit because I've actually written quicksort already. So I'm just going to copy it over and paste it in here. Okay, but let me just show you what quicksort is. So here's the program called quicksort. So I'm highlighting the name of it. And it takes a list, and here I've called it XS. Previously I'd called it LL. And what does it do? Well, if the length of the list is less than 2, then I'm done. So I return the list, XS. Okay? Otherwise, what do? I partition the list. Okay? So this is the thing, this is the piece of code that partitions the list, and I get 2 things back. I get LT and GT, and the partition algorithm works in such a way that LT is all the things less than the pivot, and GT is all the things greater than the pivot. And then what do I do with these sublists? Well, I quicksort the LT, I put it together with the pivot, and at the end of that, I quicksort GT. Okay? So this piece of code is quicksort in F#. Okay? It's really, really quite small, 6 or 7 lines of code. Okay? You could write it very easily yourself. So let's see it run. So first of all, I'm just going to run the whole thing. So I've also got 3 lists here, the list of speakers and the list of just the initials of the demos and the list of numbers. So let's run quicksort on the numbers. So I'm going to type in quicksort on the numbers, and I highlight it and press run. So you can see the numbers are initially 0, 10, 2, 4. So now I get them sorted. Similarly, I can do it for the speakers. I run quicksort on the speakers. Oops. I run quicksort on the speakers, and they're sorted in alphabetical order in this case. Okay, so again, so remember this website. You can just go there, you can write your own programs, you can run them and see how they work. Okay, so this is probably the only complicated slide I have, but just if we go through it together, we'll see how it goes. Now, quicksort is one of the fastest algorithms, given what the input list looks like. It's one of the fastest algorithms in the world. And how do people know that? Because they have used ideas from mathematics to prove that quicksort is fast. And I'm just going to give you a hint of how to prove how fast quicksort runs. So say quicksort took a list, and the length of the list was n. So there's a very small n there. And what partition will do is to divide that list n into 2 equal ones, say. Okay, this is kind of making some assumptions. So it divides it into 2 equal sublists. Say partition runs on those sublists, and it's going to divide those 2 into 2 equal ones again, and so on, until right at the bottom we only have 1 element left in every list. Okay? So what I'm showing you here is what computer scientists call a tree. It's kind of an upside-down tree because the root is at the top. And this is the recurrence tree, which tells us the cost of quicksort. What is the cost of quicksort? Well, at each level where we partition, we do n comparisons. Because we say, are you less than the pivot? Are you greater than the pivot? We do n of those. Well, remember, n is the length of the list that we give it. Okay, so we do n there, we do n there, we do n there, and so on. And how many n's are there? Well, again, some ideas from computer science tells us that a tree like this has depth log n. Okay, so maybe some of you guys know what logs are? Yes? No? Okay. So log is just a kind of a mathematical function, but it's just a function of n in this case. So if I've got log n of these, and I've got n comparisons in each, then the whole thing costs n log n. So it does n log n comparisons, which could take n log n, say, seconds to run. Okay, it's just it's a very rough idea about how to calculate the speed of your code. So maybe this is the question at the top of your mind. Because actually I talked about correctness, because I talked about using pictures to show how your code is correct. And I've talked about ideas of how you know how fast your program runs. So if you write a program to do something and I write one, we can use these techniques to work out which one is the fastest. Not by running it all the time, but actually by using mathematics to understand how fast it runs. So it's good to write correct and fast programs. But I'm not going to answer this question. I'm going to show you a picture gallery of some people who have written, who had either really great ideas or have written programs that are correct and fast. Okay, so we're going to have a little kind of a guessing game here just before lunch, and let's see how many of you can guess who these people are. So I think there's 5 or 6 of them. Okay, audience, just shout out. Very good, Alan Turing. So Alan Turing is kind of the father of computer science. And in fact, there's a demo outside at lunchtime you'll see of the code breakers. And during the war, he did some very important work in breaking the enemy's code. But he, in the early 1930s, he came up with a very, very basic idea of what a computer does and what a program is. That's Alan Turing. Anybody? Maybe somebody in the front. So this is Tony Hoare, who works at Microsoft and in fact wrote Quicksort. Anyone? You need some? Ada Lovelace, very good. So Ada Lovelace worked with Charles Babbage a long time ago. And she is the claim is that she is the first computer programmer because she wrote the programs that went into the difference engine. This is a bit of a biased one, actually. So, Bill Gates, very good. Bill Gates, a long time ago, when he was young, and this is when he just started Microsoft in Seattle. Maybe this will be a difficult one, but actually it's slightly easy because you can read his name badge. Yep, that's Donald Knuth. You can see, actually you can't read his name, but it says Don Knuth. So Don Knuth, the title of my talk today, The Art of Computer Programming, comes from a series of books that he wrote where he brought out these ideas of trying to understand how to write programs and try to understand how you know you've written the correct program and how fast it runs. So he's a very, very famous computer scientist from Stanford University. Very good. So Mark Zuckerberg from Facebook. So all of these people, they've either had really great ideas or they've written really great programs that other people use. And that's one of the really great things about programming, about being a computer engineer or a computer scientist. Okay, thank you.